welcome to our review of Module 4. This is just a brief review to get you prepared for the test and your DBA. So we're going to go ahead and get started. So the first lesson in Module 4 deals with chemical and physical changes in properties, and you were asked to really look at and identify the differences between chemical properties and chemical and physical changes. You are also asked to give examples of physical and chemical properties and changes as well. Now just remember that these are often confused. So you want to have a list of physical properties and physical changes, and you want to have a list of chemical properties and chemical changes. So make sure that you have those in your notes. Just to go over some quick examples here, really just to highlight the changes here. Physical changes, remember, are speeding up of atoms, okay, or slowing them down. So the big thing here with physical changes is the actual substance is not going to actually change. So in the case of our first example, the aluminum foil is cut in half, all right, it's still going to be aluminum foil. We've kind of changed where the atoms are, but the atoms haven't been rearranged in any way, shape, or form. Versus a chemical change where we have basically an irreversible change that has taken place, like milk going sour. Okay, we know here that because the atoms have rearranged, you cannot make milk unsour. And we can see from some of these other examples too, in other words, bread becoming toast, we know a chemical change has occurred too there because we can't go from toast to bread again. And some of the key changes that we can look for, especially for chemical changes, we can look for a color change. We can look for sometimes a smell that will change. Like most people know, when bread is toasting, you can actually smell the difference. Obviously, you can see the difference as well too. So we look for those as well. So remember, physical changes, all right, we're just basically keeping the atoms in the same arrangement. Chemical changes, we are actually changing the arrangement of the atoms around. So for lesson 4.02 in balancing equations, one of the things we want to focus in on is explaining why it's important to always balance equations. Remember, we are paying attention to the law of conservation of mass. All right, remember, matter can neither be created nor destroyed. It can only change forms. And we want to make sure that we describe coefficients. Now remember what coefficients are. They're the numbers that are in front of our compound. So for instance, if I was to write water here, all right, the 3 in front would be considered our coefficient. The 2 down here in our water would be considered our subscript. All right, so we deal only with coefficients when we're balancing equations. And that's really important to keep in mind because you are not supposed to change your subscripts. All right, now the reason why we don't change our subscripts is going back to that same example. If we change the subscript around, then we actually change what the substance is. We obviously can identify that as water, but if I was to just change the subscript into something else, we no longer have water. We have, matter of fact, we have something nonsensical here. So we need to keep in mind that while we can change this number quite a bit when balancing chemical equations, we don't want to touch this one. All right, so lesson 4.03 really gets into a lot of the meat of the module. And for this, we're identifying both double and single replacement reactions. We're also going to start predicting products, which is slightly different than balancing equations because we don't have both sides of the chemical equation present here. When we balance chemical equations, like in 4.02, we can see both the reactants and the product side of the equation. We also start using an activity series, which should be in your notes, by the way, as well. If you haven't put the activity series in your notes already, this would be a good time to go ahead and add that so you don't have to look back for it. Or search for it. You just want to have it so it's nice and easy to use for that. And we want to identify some of the commonalities between single and double replacement reactions for this lesson. So moving on to some examples here. All right. So talking about our activity series. So we need to remember that in the single replacement reaction, a reaction will occur if the individual element is the elements it's trying to replace. So, for instance, lithium is at the top here, and lithium can basically replace anything that is below it, okay? So we can work our way down. We cannot, however, work our way back up. So we see that gold is at the bottom of this particular list. And because it's so unreactive, it can't replace any of these metals that are above it. Okay, so we need to keep that in mind, that we might have some reactions where we would, it looks like a reaction should take place, but because of the activity series, we can't actually do anything with it. Okay, so in isolating our first example here, we have magnesium, we have zinc. Okay, so in theory, these should be able to switch places with each other. Okay, so but we need to check the activity series first. So I'm going to go on my activity series. I'm going to look for zinc, which is right here. All right, and I'm going to look at magnesium, which is right here. Okay, so being that magnesium is higher up on the list than zinc, they can actually swap positions for this. Okay, so moving along here. So here's some examples of what they actually look like. So we have a couple of double replacement reactions here as well as the single replacement reactions. So we can see that there's a slight difference here. So our single replacement reactions are actually on the bottom. And notice what it looks like here. We have a single element paired with a binary compound. So binary, remember, it's just a fancy word for there's two parts to it. All right. So for instance, I've got one metal here that's sitting all by its lonesome and a binary compound here. That's how we can easily identify a single replacement reaction. Versus a double replacement reaction, which is up here, you notice that both of our compounds are binary. So we've got two that are split up here. So the biggest thing is, all right, with double replacement, I know they look complicated, but remember, it's the metals that are doing all of the work here. The metals will switch positions, all right, and when the metals switch positions, they're going to form new compounds, and that will sometimes also change parts of the subscript, okay? So remember, when we're predicting products, we can change subscripts when we're predicting products. We don't change subscripts when we balance chemical equations. And the way that you really kind of want to deal with single and double replacement reactions is after you've swapped over the metals, look up the charges. Make sure, especially with polyatomic ions, make sure that the charges match up and you have a net charge of 0. If you find you have something that's uneven, you're going to want to add subscripts to it. And then once you've done that, sometimes what happens too is the reaction will actually unbalance itself once you add subscripts, which means you can finally go back at the end and go ahead and add in coefficients. So you want to keep that in mind. You want to go in that order. We don't want to skip steps when we do that. So it's basically kind of formulate, switch around the metals, all right? Look at the charges, make sure that the net charges cancel out. If they don't, add some subscripts to make sure that they can cancel out. And then go back at the end if you need to, and go ahead and add in your coefficients to finally balance it out. So it's basically a 4-step process in doing that. Okay, so in lesson 4.04, we're dealing much with the same sort of scenario, except we're dealing with synthesis and decomposition reactions. So basically, these are actually opposites of each other. Synthesis is building things up, and I'm going to put in my little bricks here to symbolize that. All right, and decomposition is going in the reverse order. We are not building things up, we're breaking them down. All right, so I just kind of put lines through just to kind of visualize something breaking up, and that kind of helps me visualize what decomposition is all about. Okay, so for this, we're looking at identifying the difference between synthesis and decomposition reactions. We're predicting the products just like we did the last time through, and we're identifying the properties of synthesis and decomposition, basically. So some examples as follows, okay? We have synthesis at the top here, all right, and notice we're starting with two kind of basic, all right, elements or compounds, and at the end we have just one product. That's the big thing here, one product with synthesis. So that's a good way to tell that it's not something like a single replacement reaction, which would have a product and something, another element hanging out on its own. So if you just see the one product here at the end, you know that that's synthesis. And we see that synthesis can take on a lot of different forms between metal and nonmetal, nonmetals and nonmetals. We have a lot of different variations of synthesis reactions. So just keep that in mind that we have several different kinds and variations of synthesis reactions. All right, remember that decomposition is the opposite, the exact opposite. So we're starting with one product here, just one. All right, and then we're going to break down into simpler formats. So for our first example here, we have basically table salt that's breaking down into a sodium ion and chlorine here. And we notice that there are many different versions of decomposition reactions as well. All right. So the big thing here is, remember, starting with one product, going into a more basic version of these compounds to kind of break them up. Okay. Just remember, it's kind of a gross example, but think about like a body decomposing. All right. If a body decomposes, it's going from very complex structure, which is a body, all right, into basically what it's going to break down to, all right, which is a much more simple, terminology. So it's a gross example, but that should be something that should help trigger your memory in looking at the structure of these particular equations. Okay, so 4.05, all right, we are just really hinging upon not just the lab, but we're looking at combustion, okay? Combustion is our last type of chemical reaction, and combustion has some very unique properties. Okay, it gives off heat and light. All right, and the biggest thing with combustion is you will always see oxygen as a reactant. So you see in our examples here, oxygen is our reactant. So within that, all right, the oxygen has to be present. Why? Think about it. Okay, what's happening in combustion? Heat or light? Light, fire, something along those lines. Think of, like, for instance, a campfire. A campfire is a combustion reaction. So if we take away the oxygen in that combustion reaction, what happens? The fire goes out. Okay, so the key thing that you want to look for is the presence of oxygen as a reactant. Okay, now remember, just like in our lab, we may have certain combustion reactions may also be synthesis. As in the case of our lower example right here, all right, we have our two basic compounds making our one product, and in that case, we can have one reaction actually classified as two in this particular circumstance, okay? The lab really entails all of the different reaction types as a review, goes through how to write out all of our equations, talks about the law of conservation of mass, and really asks you to do this kind of classification in terms of looking at a reaction that's both combustion and synthesis at the same time. Okay, so lesson 4.06 is stoichiometry, which is one that I know is intimidating for a lot of students, but really what it is it is basically using the elements of balancing a chemical equation, all right? So we've got that first element, which you learned how to do earlier on. Okay, we're going to use coefficients from our balanced equation to make mole ratios. Now, what is a mole ratio? Why are they important? Well, mole ratios have this magical property where they can turn one type of mole into another type of mole. So that allows us to do a lot of very important conversions in attaining to see how much one compound might react with another. So mole ratios become very important in that. And the biggest thing is we get them from our coefficients from a balanced equation. So balancing that equation is going to be that really important first step to make sure that we have a proper mole ratio. Otherwise, if we don't have a proper mole ratio, we're going to have an incorrect final answer. So within that, stoichiometry has a couple of other elements, okay? Besides the balanced equation involves dimensional analysis, okay? So that should be flashback from Module 1, and we worked along with it in Module 2 as well. Remember, it's just a series of setting of fractions based upon the units to get through this, all right? And we have our handy-dandy, little diagram here that can kind of tell us what steps we should take to get from one step in our equations to another. But sometimes the easiest way is really just pay attention to your units. You need to get rid of your units in a step-by-step manner, and by doing that, that can often help you complete all of the steps in the stoichiometry equation. So let me just give you an example here, okay? So in our question here, it says how many grams of sodium metal are needed to react completely with 45.6 grams of water, okay? So we're going from grams of water to grams of sodium metal, all right? So what I'm going to do in this is I'm going to check first and make sure that my equation is balanced, okay? If it's not, then I need to go and do an extra step and balance it. But I see here in my equation that it is indeed balanced. So I'm going to check that off as my first step. I've balanced my equation, or I've at least checked for it visually. And then what I'm going to do is I'm going to put my given value down here and start everything off. Now I've got grams of water, got to get to grams of sodium metal, okay? So how do I do that? Well, the first thing that I'm going to do is I'm going to convert my grams into moles. Now why do we need to do that, okay? Remember, if we want to turn something into something else, we got to get to our mole ratio. We can't use the mole ratio if we don't have moles. So that's going to really mostly be the very first step that we always want to do. So I'm going to look up the molar mass of water on my periodic table. I'm just going to look up the molar mass of hydrogen and oxygen, and remember I'm going to add those together. So that's where our bottom number comes from. That was something that was researched and looked up on the periodic table. And I'm going to put the grams on the bottom and the 1 mole at the top. And the reason I'm going to do that is to make sure that my units cancel out properly. That's how we figure out which part of the fraction goes where. So I'm going to check off here, say, oh, yep, these can cancel out here. Now I've got moles of H2O. Okay, so I've gotten closer. Now I can use my magical mole ratio to turn one thing into another. So where do these numbers come from, this 2 to 2 ratio? Remember, we're getting it from the coefficient. So I'm going to take my coefficient here, and that's going to become the first part there. And I'm going to take my coefficient for water, and that's going to go down here. And again, why did I pick which one to go on the top and which one to go on the bottom? It's based upon how it can get rid of the units. All right, so we're going to put that there, and we're going to be able to cross that out. And you do want to go through these steps. This is a really important thing. A lot of students try to take and skip these steps. I think they can do them in their head, and most of the time what happens is there is a math mistake that occurs. So I know it's a lot of extra work to write everything out like this, but please take the extra 20, 30 seconds to write out your units. It's going to make your life a lot easier. And I know what you're saying here too. Well, it's a 2 to 2 ratio. That's technically not changing anything mathematically. That's true. But what doing this step will do is it will allow you to figure out what you need to do that final conversion. So even if it's not going to change anything for you mathematically, you still want to write this step out, okay? So I've successfully canceled out my moles of H2O, and I'm going to go ahead and write in my moles of sodium here, okay? So basically, for my moles of sodium, I have that, but we're not looking for moles of sodium. We're looking for grams of sodium. So what I'm going to do is I'm going to do one last conversion and convert back to grams. And again, where did I get this number from? I looked up the molar mass of sodium on the periodic table, all right? And I put that in there, and the reason why, again, I knew to put the grams on the top and the moles on the bottom is because it allows me to cancel out this last unit. Now the big thing here is whatever is the last thing, the last unit you have, double check and make sure that your last unit matches up with what you're looking for in your question. If they do, and you've done that, then you know you've done this question correctly, okay? Now honor students, you've got a step either in the beginning or towards the end to make this happen. But you can see that the meat of the middle of this is all exactly the same, okay? Now the other big thing is a lot of students are just looking for one set equation, something where they can just plug in numbers as they feel like it. Remember that stoichiometry doesn't work like that, okay? We do the number of conversions we need to get rid of the units, but not every problem is for stoichiometry will take this many steps. Sometimes it's just one step. Sometimes it's two. So you base your conversions based upon what the question is asking you, and not from any predefined equation that you're used to just plugging numbers into. So that's my last piece on that, okay? So limiting reactants is just kind of a little bit of a twist on this. And we want to make sure that we identify when a problem is a limiting reactant problem based on the given information. We're also going to start dealing with theoretical yield and actual yield within this, as well as identifying what the actual limiting reactant and excess reactants are in a problem. So for our example here, all right, limiting reactants are what gets used up first, okay? For many of my students, I tell them it's the compound that kind of gets in the way of us hitting our theoretical yield, or that best case scenario. And then the excess is just left over. It's what you're not going to get to go ahead and use, all right? So the basic steps for this are very similar to what we use in stoichiometry. We're just basically kind of doubling the whole thing, okay? So we still want to balance our equation, just like in step 1 here, all right? We're going to identify the given amounts provided in the word problem, as well as what's being asked for us to solve here, okay? If we determine it is limiting reactants, all right, we will see that we've been given more than one reactant, okay? I'm going to show you an example here in a second. But after we do that, we're really just setting up 2 stoichiometry calculations, and then we're determining that the lower answer here, all right, is the theoretical yield, which is the amount of product that can be produced by the given amount, and the reactant produced is the lower answer. For that is our limiting reactant, okay? So just looking at an example here, and we've got some things that I'm just going to scribble out here really quickly here. So first of all, let's go through the actual classification steps, okay? We've got 3 moles of hydrogen fluoride and 4.5 moles of silicon oxide, okay? So right off the bat, we can tell that this is limiting reactant just because I have 2 reactants that I'm dealing with here, okay? So from there, same thing as in stoichiometry, make sure that this is balanced, and of course, for the sake of our time, it is balanced, okay? But remember, it's something you need to be checking for. And then I'm going to just take these numbers and slide them down over here. And then I'm going to do some basic stoichiometry just to see how many moles we would be getting here. Okay, so lowest number going to be theoretical, all right? And because it's the lowest number here, we know that the reactant that we use to get this lowest number when we did that is going to become the limiting reactant, okay? So this is what we could potentially get here. All right, so last but not least is the lab that you just did, all right, where you're identifying actual yield and theoretical yield with some stoichiometry thrown in as well, and we're going to determine the percent yield and the theoretical yield. Remember, actual yield is what you actually get during the experiment. Theoretical is what you could potentially get on the most perfect day ever, which almost never happens. All right. Now, the equation for it is actually pretty basic, okay? You're going to use percent yield equals actual divided by theoretical and multiply it by 100, okay? So the big thing is you do want your actual yield to try to get as close as it can be to the theoretical. If the actual yield is very, very low, of what one would look like. All right. So we have 9.8 grams of magnesium metal reacting with excess hydrochloric acid and 29.8 grams of magnesium chloride produced by the reaction. And it's asking us what the percent yield would be. So this is, again, it's very similar to what you did in your lab. Again, check, make sure that your equation is indeed balanced. That's step number one. And then we're going to go through here, and we're just going to set up a stoichiometry equation we need to get from grams of magnesium, all right, just like in our problem here, all right, and we need to get to and work with grams of magnesium chloride in here. And we're also going to be dealing with that in this scenario here. So what I want to make sure is I have this matching up here. And basically, again, if you look at this, this is just stoichiometry. All right, we're just going through the steps where we're converting grams to moles. We're going to cross everything out. We're going to use the mole ratio. And again, look here, not going to change anything mathematically, but it's going to allow us to go ahead and complete that middle step there to turn one type of mole into another type of mole. And again, using molar mass to convert from magnesium to magnesium chloride, okay? And that's going to give us our theoretical, all right? And then for actual, all right, we're just going to go ahead and since it was so nice that they actually gave us that here, which sometimes you do get lucky and they give you that without any calculations needed. We're just going to take that. We're going to put it at the top of our equation. And then we're also going to take our answer for theoretical. We're going to plug this in here, and that's going to give us our percent yield, okay? So this one, not too difficult mathematically, especially as we've been doing stoichiometry for a while. So thank you. This was our brief review of Module 4.